Hey chemistry kids, Campbell here. It's finally time for our last video on bond, chemical bond. And today we're going to talk about VSEPR theory. How exciting! So we're going to use VSEPR to predict what molecules look like in 3D. So we've looked at molecular formulas, right? You've been writing those for a while with nomenclature. We just did structural formulas, which are Lewis dot structures. But now we're going 3D. So we're going to talk about molecular geometry and shape. And what that is how the molecule actually looks like on a 3D level. So what does it look like in real life? Well, the way we figured this out is using this thing called VSEPR theory. VSEPR theory is valence, shell, electron, pair, repulsion, theory. Wah! Basically, what it says is that electrons, which are negatively charged, don't like each other. Right? The opposites attract, but likes repel. And so they try to get away from each other as far as possible, these pairs. So anytime the molecule actually sets up in space, those pairs, those bonding pairs, and the lone pairs try to get as far away from each other as possible. Now, for this unit, you're going to need the last page of your homework. The last page of your homework has this wonderful table, and we'll be using this to determine the geometry and shape of molecules. So I know you got to take notes, but you're going to need this page too. Now, if you look at this page, you'll see that there are three types of geometry that we're going to study in this class. There are actually more, but for this class, we're just going to do these three. They're linear, trigonal planar, and tetrahedral. But there are more shapes. So for shapes, there's linear, trigonal planar, bent, which is also called angular, tetrahedral, trigonal pyramidal, and bent, which actually looks just like that bent. From a 3D standpoint, right, they kind of look like this. So here would be linear. Now, any molecule that's just two atoms, like say N2 or O2 or carbon monoxide, would look like this, right? Linear is the only chance. 2 points make a line, right? But something else like carbon dioxide, which just has two atoms bound to the carbon, they're going to get as far away from each other as possible. And so carbon forms a linear shape. Something that's trigonal planar, all the atoms are in bonds, and in 3D it looks like this. If it's bent, that means that one of these groups is actually just a lone pair of electrons. And so we don't draw that when we talk about shapes, we kind of ignore those in our shape. So that's why we call this shape bent. For tetrahedral, we have three possible shapes. We have tetrahedral, which looks like this. All the electrons all these bonded pairs are as far away as possible. Trigonal pyramidal looks kind of like a pyramid with, this is just the lone pairs, so sometimes we just ignore that when we're looking at the picture, so it just is like a pyramid. And then again, bent or angular looks just like this, except of course these have two lone pairs and they're in this 3D representation, but we usually don't put them in a 3D representation, which is why we call this bent. So let's talk about how you figure out what's what. Well, it's the number of groups around the central atom that determine the geometry. So if you look on your little sheet here, the first thing you'll see is this column that says pairs. The pairs are what determine the actual geometry. So let's take a look at some steps to determine molecular shape. So we're going to start with carbon dioxide. If we write the Lewis structure for carbon dioxide, which we did in our last video, it would look like this. So carbon dioxide has two double bonds on either side, and then our oxygen has two lone pairs. But it's the central atom that we care about when we're looking at geometry, not the outer guys. So what we're going to do is we're going to count the groups around the central atom. This just has two groups. Now, I know you're like, but Mrs. Campbell, those are double bonds, and double bonds have two pairs, which is 4 electrons, so why wouldn't that be like 4 groups? Well, anytime it's a double bond or a triple bond or a single bond, it just counts as one group. So I have 1, 2 groups around the central atom. So when I go to this spreadsheet, that you have on in your homework, you'll see that two groups, that's the same thing as number of pairs, is a linear shape. So you're going to, for now, consult this table. So pairs here means how many groups are around the central atom. There's two, so it's linear. And your only choice for shape for linear is also linear. So we're not even going to talk about shape. That's our next one. So for our geometry and our shape, we have a linear molecule because there's only two groups around the central atom. Now, the total number of electron groups around the central atom determine the geometry. So we just looked at what was around the central atom for carbon dioxide. But the number of bonded versus lone pairs determine the shape. So if you look at your table here, right, after we get through geometry, we see bonded pairs and non-bonded pairs. So non-bonded is my lone pairs. That's what determines the actual shape of the molecule. So let's take a look at another example. So let's do something that has three groups, because now shape will differentiate. All right, so let's look at sulfur trioxide. When we drew the structural formula of sulfur trioxide, which you actually did in your Check Your Learning practice from the last video, your structure would have looked like this. So what we do, right, is we count all the groups around the central atom. So we have 1, 2, 3. Remember that a double bond counts as 1. And I go to my chart and I find 3 pairs, so that's groups around the central atom, and it's trigonal. So this shape is trigonal from here. Next, though, I have to count all the electrons that are bonded and the ones that are in lone pairs. So when I do that, I go here and I see that every single electron around the sulfur is in a bond. So they're all bonded pairs. So when I go to my little chart here, I look bonded pairs, there's 3. There's nothing that's lone. So this is trigonal, trigonal. So it looks like this. So this sheet is the key to this unit, or this part of the unit. Let's try another trigonal. So how about sulfur dioxide? If we draw the Lewis structure for sulfur dioxide, it looks like this. So when I count my groups around the atom, this time I actually have a lone pair. So I have this bonded pair, and I have a lone pair. So for groups around the central atom, I have 1, 2, 3. 3 groups. So 3 groups, according to the sheet, is trigonal. Now I look at bonded versus non-bonded, or lone pairs. So I have 2 that are in bonds, and I have 1 lonely pair up here. So when I go to my sheet here and I look at this category, I'm looking for 2 bonded and 1 non-bonded. And you can see that the shape for that is angular or bent. So it looks like this. So the sheet, count the number of things around the central atom, and that'll give you the geometry. Look at how many are in bonds and how many are lone, and that tells you the shape. All right, let's try another one. Let's do something with 4 groups. All right, so here is, it's actually called methane, if we're talking organic, or carbon tetrahedride. So if I drew the Lewis structure, which again you did in your Check Your Learning practice for the last video, it would look like this. I count all of the groups around the central atom, and I have 1, 2, 3, 4. So according to this table, 4 is tetrahedral for a geometry. Next, we look at the bonded versus non-bonded. Well, we can see that every single set here is in a bond. So when I go to my table, I see 4 bonded, 0 non-bonded, which makes this tetrahedral. Now, do you notice a theme here? If everything is in a bond, the name of the geometry is the name of the shape. Well, that helps because you're going to have to memorize this table, and maybe that'll help you remember tetrahedral, tetrahedral if they're all in bonds. And so this is what a tetrahedral atom looks like. Let's do another tetrahedral. I have 3 choices for tetrahedral. All right, what about water or dihydrogen monoxide? Here would be my Lewis structure for hydrogen. These are two lone pairs. I could have put another lone pair here, I guess. Anyways, we have 1, 2, 3, 4 in my Lewis structure for water. So if I count all of the groups, that's 4, which makes it tetrahedral. But now I count bonded versus non-bonded. Well, it looks like I have 2 that are in bonds, and then 2 of these groups that are lone pairs. So when I go to my table, I see 2 and 2. So 2 bonded, 2 non-bonded, and I see that that shape is angular. So it looks kind of like that. Almost kind of looks like a Pokemon. All right, one more. Okay, so I went a little out of order. How about NH3 or nitrogen trihydride, which is ammonia? The Lewis structure would look like this. So when I count all the groups around my central atom, I have 1, 2, 3, 4, which makes the geometry tetrahedral. I count all my bonded versus non-bonded, so I have 3 that are in bonds, and I have 1 that's all lone. So I go to my table, I say 3 bonded, 1 alone, and that makes the shape of a pyramid. So that's pyramidal. So tetrahedral for geometry because there are 4 groups, but only 3 of those are in bonds, so that's pyramidal. Last thing I need to talk about is molecular polarity. Now remember when we talked about covalent bonds, we said there were polar and nonpolar covalent bonds. And we said that the ones that were polar were also called dipoles. Well, a molecule can actually have polar covalent bonds and be nonpolar. When we look at molecular geometry, a molecule is polar if it has polar bonds, but it also has to be lopsided. So molecules can either be polar or nonpolar. How do you know? Well, first you can go and look at your little table, because there's a column in your table after the shape that says polarity. Anything that doesn't have any lone pairs. So when everything is in a bond, it is nonpolar. But if we have lone pairs and we have polar bonds, then we have a molecule that's polar. So here is an example of NH3, right? We just talked about NH3, and NH3 had that, it was tetrahedral, but it was pyramidal. And so that means there was a lone pair up here. So nitrogen and hydrogen has polar bonds, and because the molecule is lopsided, it's a polar molecule. Now, something that has polar bonds but is not polar is something like carbon tetrachloride or carbon dioxide. This shape is linear, and all of the molecules are in bonds, or sorry, all the electrons are in bonds around the central atom, so it's not lopsided, so it's not polar. Same thing here with my tetrahedral shape. Even though the bonds are polar, it's totally symmetric. So even though chlorine is hogging the electrons, they're all hogging, and because they're evenly distributed, the net effect is not polar. So first start, use your table. But what you can see is that anytime something has lone pairs, it has the chance of being polar if the bonds themselves are polar. And remember, you determine that by electronegativity difference, right? 0.5 to 1.7. Got it? Cool. So try some of the extra practice on the VSEPR theory, and I'll see you in class.